Now, the first image from the world's most powerful space telescope, James Webb, is here.
This is the first time something like that is observed, where there is a glow ahead of the object towards the sun.
The arrival of 3I Atlas into our solar system was already extraordinary. An interstellar visitor, hurtling in at enormous speed, carrying chemical signatures unlike any seen before. But imagine if it weren't entirely alone. Imagine if, in the dark reaches of space that it traversed before our sun's warmth could touch it, there lurked 9 hidden companions, small, obscure bodies locked in its wake, bearing silent witness to its interstellar journey. The idea that the James Webb Space Telescope JWST might have glimpsed them adds a layer of intrigue. What if these 9 objects are escorting 3I Atlas, trailing behind or alongside, sharing the same path or bound in a subtle gravitational dance? The implications of such a configuration would ripple through our understanding of not just this visitor, but of the architecture of interstellar debris, the remnants of other star systems, and the processes that send such relics drifting into our solar neighborhood. Before we start, smash the like and subscribe buttons for more updates. From the moment 3I Atlas was discovered on July 1, 2025 by the Asteroid Terrestrial Impact Last Alert System Atlas survey in Chile, astronomers recognized its oddness. Its hyperbolic trajectory meant it was clearly from another star system. Observations soon revealed a rich coma laden with carbon dioxide, water ice, carbon monoxide, and other compounds. Yet the notion of 9 discrete objects accompanying it would open questions about fragment survival, capture, companion formation, and the dynamics of interstellar wanderers. The idea of companions escorting such a visitor raises immediate questions. How did these objects come to be associated with 3I Atlas? Did they originate in the same parent star system, forming as a mini cluster of planetesimals that were ejected together? Or did they become bound during the journey, perhaps captured from some other system or impressed upon by a passing stellar interaction? If JWST or other instruments were to detect them, by observing faint trails or shadows in infrared or subtle deviations in the trajectory of 3I Atlas itself, it would point to a far richer and more complex environment than a single lone wanderer. The dynamics involved are fascinating. 3I Atlas approaches the Sun at a speed far beyond typical solar system objects. It is inbound at a heliocentric distance of about 3.32 AU when JWST's NIRSpec observations were made, and the molecular data show an unusually high CO2-H2O mixing ratio of about 8, one of the highest ever recorded in a comet. If 9 small companions are present, they must share or nearly share the trajectory, or be in a trailing arrangement perhaps slightly offset from the main body. That suggests they were likely ejected simultaneously, or were once gravitationally bound, perhaps loosely, and are now being carried along in the same flight path through interstellar space and into the solar system. If JWST has in fact detected such companions, the detection mechanism might involve faint infrared signatures beside the main coma of 3I Atlas, or subtle distortions in the dust and gas envelope. The faintness of small bodies in deep space means any detection would be challenging. JWST's infrared sensitivity is unparalleled, allowing the detection of gas species and dust and features in comets at great distances. But to pick out 9 faint objects would require careful analysis of images, background subtraction, and recognition of objects moving in concert with the primary body. If that analysis turned up 9 such bodies, the next step would be to determine their sizes, composition, mutual separations, orbital relationships if any, and relative velocities. The presence of 9 companions would have strong implications for our understanding of how interstellar objects' ISOs are ejected and what they carry with them. Until now, only 2 interstellar objects have been confirmed, 1I Oumuamua 2017 and 2I/Borisov 2019. 3I Atlas is only the 3rd confirmed thus far. The discovery of companions would suggest that such objects might travel not as isolated lone wanderers, but sometimes as small groups. If a parent star's debris disk or planetary system ejects material, it may come off in clusters rather than as single items. That would inform models of planetesimal scattering, ejection dynamics, and the broader picture of how material from one star system can seed another's region. In terms of composition and surface processing, The fact that 3I Atlas shows a CO2-rich nucleus suggests it formed under conditions somewhat different from typical solar system comets. The high CO2-H2O ratio may point to formation near a CO2 ice line, or to prolonged exposure to higher radiation. If the companions share that composition, then we might have 9 additional samples of that alien environment, each offering its unique window into that system's chemistry and evolution. It elevates the discovery from a singular specimen to a miniature sample set. It raises questions. Do all 9 share the same composition, or do they show variation? Are there differences in volatile content, dust-to-gas ratios, radiation processing? Their mutual comparison could refine our understanding of the parent system's conditions, its ejection event, and the subsequent journey through the galaxy. The possibility of 9 escorts also prompts reflection on long-term stability. How do these small objects keep pace with the main body? Without strong mutual gravity, they might drift apart over time. The fact they remain associated suggests either the ejection occurred fairly recently in cosmic terms, or that their configuration is more stable than expected, perhaps due to a shared velocity vector and minimal perturbations. Furthermore, entering the solar system means they now encounter the sun's gravity, solar radiation pressure, solar wind, and the dynamic interactions of our system's gravitational field. That could cause separation, fragmenting, or dispersal over time. If these 9 bodies remain in proximity, they tell us the window from ejection to solar system entry was narrow, or that escape from their original system and travel through interstellar space has not significantly separated them. In terms of observational strategy, detecting 9 small bodies traveling with 3I Atlas would push the boundaries of current instrumentation. JWST's powerful optics and infrared instruments allow detection of faint thermal signatures and compositional analysis of comets even from great distances. The detection claim of 9 escorting objects would hinge on multiple epochs of observation, high signal-to-noise images, background star subtraction, and tracking of proper motion consistent with the primary comet. Because such objects would be faint, possibly dark and small, distinguishing them from background asteroids, faint stars or noise artifacts would require excellent calibration and confirmatory observations. If confirmed, follow-up observations with other telescopes, ground-based observatories, radar, or even space telescopes would be warranted to track their trajectories and measure relative positions. From a theoretical standpoint, if 3I Atlas did carry with it 9 smaller bodies, that suggests the parent system ejected a group of planetesimals, perhaps during a close encounter with a massive body, or during the chaotic early phase of planetary system evolution. The ejection could have occurred when the parent star passed near a giant molecular cloud, or through interaction with another star in a dense stellar environment, causing the release of multiple objects on similar escape trajectories. This in turn would support the idea that interstellar comets are not solo drifters, but may come in families. If so, our catalog of interstellar objects, even though small at present, may need to consider the possibility of grouped arrivals, altering the statistical models of ISO detection. Moreover, if 9 objects are present, they might carry different surfaces, different volatile abundances, and different surface processing histories. Some might have been closer to the parent star, others farther away. Some might have experienced heavy radiation, others more shielding. That heterogeneity would offer scientists a richer dataset, 9 mini-analogs rather than 1. Through spectroscopy, scientists could compare infrared signatures, dust emissions, volatile outgassing patterns, and surface reflectance properties. If any of those 9 objects are more pristine, less processed than the primary, then the entire discovery becomes a treasure trove. We might be looking at a miniature sample return mission across multiple bodies without launching a spacecraft. The implications for solar system science are broad. First, the notion of extrasolar material entering our system not only as isolated objects, but as clusters opens the possibility that fragments of other systems could deposit in the solar system more frequently than thought. If 3I Atlas arrived with companions, then perhaps previous interstellar visitors likewise may have been accompanied by smaller companions, but we simply lacked the sensitivity to detect them. That would reshape how we search for ISOs. Rather than scanning for a single bright object, we might look for associated faint trails or trailing bodies along the same trajectory. Secondly, the composition of these objects might preserve chemical signatures of star-forming environments unlike our own. Through spectroscopy of the companions, we might detect isotopic ratios, ice phases, dust properties, and volatile inventories that reflect environments in other parts of the Milky Way. And those data would feed back into our models for planet formation, solar system evolution, and galactic material exchange. The hypothesis of 9 escorts also provokes thoughts about the fate of such material. As the cluster of bodies passes through our solar system, solar radiation begins acting on them, sublimating volatiles, altering surfaces, producing comets and tails. 3I Atlas itself is already showing active behavior, the sublimation of CO2 and other volatiles as it approaches the Sun. If the companions are smaller, their activity might differ. Some might remain inert, others show faint coma, and perhaps some might fragment entirely. Observing them provides a natural experiment in how interstellar small bodies respond to solar heating, how dust and gas are released, how small bodies break up when newly arrived in a star system other than their own. From a broader vantage, the arrival of these objects, if indeed multiple bodies traveling together, suggests that our solar system is not isolated but is open to visitors not just in isolation but as part of a stream. The galaxy is full of star systems ejecting debris, and some of those debris strings might be threading through our region of space. The fact that 3I Atlas is entering now, and perhaps accompanied by 9 others, suggests we might be moving through or near such a stream. If so, further searches might reveal more objects with similar trajectories, or traces of older companions dispersed along the path. It invites the idea that our solar system may periodically be crossed by previously unseen streams of interstellar debris, each carrying fragments of other star systems, and that those fragments may come in clusters or families. Another implication resides in planetary defense and long-term monitoring. If interstellar objects sometimes arrive not singly but as groups, then the possibility of multiple objects entering the solar system from one ejection event might raise interest in broader monitoring strategies. Even though 3I Atlas poses no threat to Earth, the detection of 9 additional objects, however small, would mean that ejected material from other systems can arrive in numbers and with uncertain sizes, velocities, and trajectories. We would need to refine our detection networks to look earlier, deeper, and for trails of faint bodies accompanying known ISOs. The recognition of escorting objects could also open the possibility of targeted interception or mission planning. If a cluster is detected early, one object might be targeted for closer study, while others serve as comparative specimens. On the scientific side, having multiple bodies from the same ejection event means we can test hypotheses about the origin environment more robustly. For example, does the CO2-rich natal environment of 3I Atlas apply to its companions? Do they share the same ratio of CO2 to water, or are they differentiated? Do they show the same isotopic signatures, dust grain sizes, ice phases? If not, that suggests heterogeneity even within a single ejected parcel, which in turn influences how we think about the evolution of planetesimals in protoplanetary disks. The companions might preserve different exposures to cosmic radiation, or different thermal histories, giving us a mini laboratory for studying the diversity of planetesimal populations in other systems. Furthermore, the presence of companions impacts trajectory modeling. When 3I Atlas entered the solar system, its path is hyperbolic, not bound to the Sun, but passing through. If 9 companions accompany it, then mapping their orbits and divergences would give insight into how tightly bound they are to the main body, how much dispersion has occurred, and what tidal or gravitational influences they've undergone. Perhaps some will separate further, diverge more quickly than the primary, or even be lost as free drifters themselves. Tracking them over time will allow us to watch the evolution of an interstellar cluster entering a star system, something never before observed. The potential for samples is tantalizing. If any of the 9 companions are less active, less processed, perhaps smaller and thus less heated by the Sun, they might preserve ices or materials closer to their pristine state. That holds immense value. Each could be a frozen time capsule from another system, carrying records of that system's formation epoch, chemistry, and processing history. Instruments like JWST or future missions might target them for infrared spectroscopy, dust detection, tail morphology, and composition. The data could refine our understanding of where and how those objects formed, perhaps in a region of their star system rich in CO2 ice, or under radiation environments unfamiliar to our own. The mere possibility of such an escort raises philosophical questions too. If interstellar objects sometimes travel in clusters, then our solar system has been penetrated not just by lone wanderers, but by small fleets of material from elsewhere. That fosters a broader cosmic perspective. We are part of a galaxy where matter exchanges between star systems may be more common than we thought. Debris ejected from one system can drift for eons and eventually pass through another. The scientific and human significance of that cannot be understated. Each interstellar object is not only a curiosity, but a messenger from another star, another time, another place. In a practical sense, if these 9 objects are confirmed, they would galvanize efforts to locate and study them quickly. The window for observation is limited. As they approach the sun, solar heating will drive activity, dust will obscure surfaces, and some might fragment or disintegrate. Observational campaigns would need to map their positions, identify relative motion, capture spectroscopy and imaging, build light curves and monitor tail evolution. Instruments tuned for infrared, ultraviolet visible dust flux and gas emissions would all be mobilized. The data gathered would expand our catalog of extrasolar material by an order of magnitude, 10 bodies instead of 1. The theoretical ramifications ripple outward. If clusters of ISOs are possible, models of stellar system evolution must account for multi-object ejection events. The dynamics of planet formation, resonances, scattering, binary stars, and cluster ejection must be reconsidered. We might need to rethink detection probabilities. Rather than a Poisson process of single objects, we may have bursts or streams of material. That influences how we design surveys: wide-field infrared, deep sky, high cadence, looking for trailing objects in similar trajectories as known interstellar intruders. The 9-object escort scenario also compels us to examine the end state of such bodies. After passing through the solar system, what becomes of them? Do they get decelerated, slowed, perturbed? Likely they exit back into interstellar space, but with altered trajectories. If a cluster passes through a star system, solar system interactions may strip dust, drive sublimation, fragment them, or even capture one into a distant solar orbit. While capture is unlikely due to high velocities, the interactions might leave traces. Dust trails, solar wind interactions, secondary ejecta. The presence of 9 companions increases the chance of such interactions simply by the numbers. In sum, the idea that JWST might detect 9 hidden objects escorting 3I Atlas is more than an intriguing twist. It is a window into a deeper, richer interstellar process. It suggests that when an object crosses from one star system into another, it may not come alone. It invites a rethinking of how we detect and study interstellar visitors, how we interpret their composition and trajectories, and how we understand the flow of material across the galaxy. If confirmed, those 9 companions would multiply our opportunity to examine extrasolar material, offering multiple records of a distant environment, multiple vantage points on formation, composition, and evolution outside our solar backyard. They would provide not just a single specimen of interstellar matter, but a small entourage, an entire entourage passing through our cosmic neighborhood. If the James Webb Space Telescope truly detected 9 hidden objects accompanying 3I Atlas, the revelation would not simply redefine a single astronomical event. It would transform how humanity interprets the movement of matter between stars. Each of these faint companions could represent a fragment of a greater cosmic mechanism that binds the galaxy in a web of shared material exchange. Their arrival together in our solar system could mark the first observational evidence that interstellar debris travels in coordinated formations, not as isolated wanderers. This idea challenges centuries of perception about the universe's structure, turning what was once believed to be random into something potentially systematic, a quiet choreography of celestial drift across light years. The technical significance for JWST cannot be overstated. Detecting small, dim objects against the background of deep space requires an almost impossible level of precision. The telescope's ability to discern faint thermal signatures allows astronomers to trace not just the brightest bodies, but the faint echoes that follow them. The infrared sensitivity of JWST might have caught minute temperature variations, tiny glowing dots moving in lockstep with 3I Atlas, too consistent to be chance. This would mean the telescope has achieved what no previous observatory could, resolving not just an interstellar traveler, but its hidden entourage. Such an achievement would highlight the immense power of space-based infrared astronomy to uncover structures invisible to even the largest ground telescopes. Astrophysicists would immediately begin constructing models to explain how such a cluster could survive the brutal journey between stars. Interstellar space is a realm of radiation, microcollisions, and temperature extremes. For 9 small companions to remain coherent, even loosely associated, across millions or billions of years, some stabilizing mechanism must exist. Perhaps magnetic interactions, shared outgassing histories, or synchronized ejection velocities preserved their relative motion. If this turns out to be the case, it would hint at a physical principle not yet fully explored, an interstellar version of co-migration that allows groups of objects to traverse the galaxy as miniature flotillas. It might also imply that our solar system has, over its history, been brushed by such groupings many times without ever noticing. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the James Webb discovering hidden objects near 3I Atlas? We want to hear from you. Thank you for watching, and see you next time.